A warm welcome to all the students. Today we are going to see one of the last concepts in the fourth unit, that is universal Turing machine. Okay. Now before I begin with this topic, let me tell you that ever since your first lecture in the first unit, I have been always telling you that a Turing machine is the most powerful of all the Turing machines. Okay, and in this particular concept you are going to understand why I say so. Okay, now the idea of this universal Turing machine, it is similar to the stored program concept given by von Neumann in 1943. Von Neumann came up with the architecture of computer in 1943, in which he also specified a concept called as stored program. Okay, now what happens is in your computers, if you consider, okay, there will be one program. For example, there is a music player who does one particular specific task, for example playing music. So that's a stored program. There might be another stored program, for example say calculator, who will be doing only one specific task of calculating some computations. Fine. Then the third stored program, for example you have something like the date, time and date app. Okay, so that will be concerned only with time and date. Okay, and some appointments you can schedule and all that thing. Okay, so each of these stored programs that are there in our computers, okay, they have only one particular or a specific use. They are designed for only that one task. Okay, now when you see computer as a whole, computer contains all these small programs, stored programs, which are bundled in itself, and that's why we say that computer as a whole is a multi-purpose machine, because within the computer you can store different programs and each program can perform a specific task. So when you consider the computer as a whole, it will appear as a tasking application, or the application which performs multiple different tasks. Okay, now universal Turing machine was designed by Alan Turing in 1936, much before von Neumann came up with the architecture, okay, and a concept of stored program. Now before I begin with what exactly is a universal Turing machine, okay, so far we have seen Turing machines. Okay, for example, we have seen a Turing machine to detect whether a given string is a palindrome. Okay, now this Turing machine will only detect whether a given string is palindrome or not. We have also seen a Turing machine that does some specific computation, for example say incrementing a number. Now this Turing machine will only increment a number. Given an input, it will always give the output which is incremented number. We have also seen a specific Turing machine that does something like addition of two numbers and so on, right? Now, each Turing machine has a specific activity. It does only that particular specific task. So you can relate these Turing machine, each individual Turing machine, with a stored program, okay, in the computer. Now what universal Turing machine does? Universal Turing machine, or UTM as we call it, okay, universal Turing machine or UTM as we call it, what it does is, this universal Turing machine, it has a capability of storing multiple Turing machines within itself. So in UTM we just call it as TU, a number of Turing machines and their inputs are stored, so that TU equal to T1, T2 up to Tn, where T1, T2 up to Tn, they are individual Turing machines capable of doing some specific activity or some specific task. Okay, so now each Turing machine solving a problem can be now considered equivalent to a program, and universal Turing machine that contains or that includes all those Turing machines itself is equivalent to a computer, right? Now Turing machines, what Alan Turing did was, he tried to encode this Turing machine. See, the question was, Alan Turing in 1936, after proposing his universal Turing machine, he also came up with a setup, electronic setup of the universal Turing machine. And since he was trying to implement it, the electronic setup, Basically, he was trying to implement hypothetical computer, which was proposed by him. Actually, during those days, or even now, whenever we deal with electronics, okay, the language that we use is machine language or hardware based language. Okay, so one question was in front of him: how to represent these Turing machines, the theoretical Turing machines, how to represent these individual Turing machines in terms of machine language, strings of zeros and ones. So then they came up with one function and they said it is a encoding function E. So Turing machines are stored in universal Turing machine by using an encoding function E. Okay, and this encoding function gives a representation for each tape symbol, for each of the tape symbol, for each of the state, for each of the direction of pointer movement. For each of these, there is a formula that basically encodes that particular activity into a string of zeros and ones. So these are the formulas, encoding function formulas to encode each and every smallest component of Turing machine into a strings of zeros and ones. Okay, let's go one by one. The first one, encoding function for a blank symbol. You may write it as delta. Your textbook writes it as square, so you can write it as a square. Or some textbooks use it as a capital B. Some textbook uses it as hash. All these blank symbols. Okay, the encoding function for the blank symbol is a single zero. Okay, so whenever encoding function is applied for blank symbol, you will get single zero as a string. Now, encoding function for input alphabet. Okay, for example, suppose the given input alphabet is A, B. Okay, now this A, B, some people can also write it as B, A. Although we don't write this frequently, but you can also write this as B, A. Okay, so now whenever I write A, B, you consider this, whenever I write A, B, suppose input alphabet given to me is A, B, you will say that in the given input alphabet, okay, A is the first symbol and B is the second symbol, correct? Now if you represent this input alphabet like this, the other way around, then also you can say that this B is the first alphabet, first symbol in the alphabet set, and this A is the second symbol in the alphabet set. Okay, so when I say first and second, I am actually writing what is index value, I equal to. Okay, so for A, index value is 1 because it's a first symbol in the alphabet set, and for B, I value is 2 because it's a second symbol in the alphabet set. So using this encoding function in general for any symbol AI in the alphabet set where I is the index position, you get the formula that we use is 0 raised to I plus 1. So in a simple words, suppose your alphabet set sigma has A, B, then encoding function value for A will be, since A is the first symbol, it will be 0 raised to I plus 1, and in my case I will be 1 because A is the first element in the input alphabet set. So wherever I is there, I will substitute that with 1, and what you are going to get is 2 zeros, string of 2 zeros. So that is how first input symbol in the alphabet set is first symbol in the alphabet set is encoded. B is the second symbol in the alphabet set. For that, for B, I is 2. So 0 raised to I plus 1 formula, you will be writing it as, wherever there is I, you will be replacing it with 2 now. So since I is 2, 2 plus 1, so you will get 3 zeros. So encoding for the second symbol in the alphabet set B will be 3 zeros, and so on. So this is how, this way, using this formula, you can encode input alphabets in the alphabet set. Okay, a very simple formula. Let's continue. So this is how input symbols in the alphabet set can be encoded. If you go further, now these three formulas are used for encoding the states in the Turing machine. Okay, whenever we deal with Turing machine, you have something called as HA. It's a halting state. Halt with accept. Okay, it is halting by accepting the given input state. So this is HA. Also in some Turing machines you also have something called as HR. That means halt with reject. So you halt the machine by rejecting the string HR. Okay, you will not frequently find HRs in R diagrams, but for example, suppose they have given a Turing machine diagram wherein there is HR, you will have to consider this. So encoding for HA, halting state HA, halt with except, is single zero. Encoding for halt with reject is 2 zeros. Okay, encoding for any other state Qi is 0 raised to I plus 2. Okay, now let's consider that in a Turing machine, Q is say Q0, Q1, Q2. Say there are 3 states, Q0, Q1, Q2. Okay, now whenever you say Q0, this will be the first state, this will be the second state, and this will be the third state. So I value for Q0 will be 1, I value for Q1 will be 2, I value for Q2 will be 3. So using that formula, what will be the encoding function value for the state Q0? The formula says encoding for Qi, where I is the index position, is equal to 0 raised to I plus 2. So for Q0 it will be 0 raised to I plus 2. And what is I value for Q0? It is 1, because Q0 is the first state in the set of states. Okay, so 1 plus 2. So the answer of this will be 3 zeros. So encoding for Q0 will be 3 zeros. Similarly, encoding for Q1, if Q1 is the second state, as I told you, will be 0 raised to I will be 2 here. So 2 plus 2. So the answer to this will be 4 zeros. That will be encoding for the state Q1 and so on. So this is how you are going to use the formula and find the encoding function values here. Okay. Further, also the head movement, that is left, right and stationary movement, for that also there are encoding functions. Encoding function for a stationary movement or stay on option is single zero. Encoding function for left movement, moving one place to the left, is 2 zeros. Encoding function value for the right movement is 3 zeros. Small t1, okay, suppose the transition is this, small t1, the first transition is this, del of p comma a equal to q b d. Okay, that means from particular state from particular state p, on reading a as input, from particular state p, on reading a single a as input, okay, we go to state q. From particular state p, on reading a as input, we go to state q. Okay, and then the new symbol is b, input symbol is b on the tape, and the head movement is defined by capital D. So capital D can just a placeholder, it can be left movement, right movement or stationary movement. Okay, so each transition of this type, okay, can be converted using encoded function using this formula. So encoding for the transition T1 is, what you do, first you write encoding for P. For P you write encoding for P. P is a state. So you have already seen how to encode each state and you must have done it so far, okay, before applying this formula. So encoding of P. Then there is a separator value 1 that separates each of these encoding functions, individual encoding functions will be separated with 1. So encoding of P you write, then 1, then encoding of A, the next value, then again 1, then encoding of Q, again 1, then B is there, so encoding of B, then 1, then D is there, so encoding of D ending with 1. So this is a formula that we use to encode each transition. Now Turing machine T1, let's say T1 is one of the Turing machines in universal Turing machine. Turing machine will have number of transitions, right? This is just one transition. So this way you will apply this formula for each and every transition of the Turing machine capital T1. So finally the Turing machine capital T1 itself is encoded using the following formula. So encoding for Turing machine T1 is encoding of Q0, where Q0 is what? Q0 is the start state of the Turing machine, separate with 1. Then encoding of T1, which is the first transition of the Turing machine, separate with 1. Encoding of T2, which is the second transition in the Turing machine, separate with 1, and so on. Go on doing this till all the transitions are over. So finally it is encoding for TK, kth transition in the Turing machine, and finally you write 1. So this is how you can encode the Turing machine T1 itself. Okay. Finally, the universal Turing machine, which contains different Turing machine itself, can be encoded using the following formula. So Turing machine itself can be encoded using following formula. So you write 1, then encoding of T1. So you know this formula. So this formula does what? It encodes the Turing machine T1. So that big string that you get, you are going to write here. Then again 1. Then again in the same manner, encoding for second Turing machine T2. Then again 1. Then encoding for third Turing machine T3, and so on. Finally encoding for last Turing machine Tk, ending with 1. So this is the formula that you use to encode the Turing machine itself. The universal Turing machine itself, where capital T1, capital T2, capital T3 up to capital Tk, they are the each individual Turing machines present in Tu. Now let's solve an example. So this is a Turing machine that is given to us, and we are asked to encode this Turing machine. Okay. Now encoding the Turing machine, we have to use the formulas that are given to us. Now the very first thing what we are going to do is all these 7 transitions which are there, 1, 2, 3, 4, 5, 6, 7, we are going to write them down in this particular manner, so that applying the encoding function for these individual transitions would become easy. Okay, so let's start. So what you have to first do is, if this Turing machine is given, you have to first convert each transition, visual transition, into the textual transition. This. Now let's start encoding the Turing machine. Encoding for delta, blank symbol, it is always 0. Now encoding for input alphabet. Now see here, sigma, as you clearly can see, sigma is 0, 1, and the number of states which are present, capital Q, is Q0, Q1, Q2 and H. These are the set of states which are present. So encoding for delta. Next we need to find out encoding for the input alphabet set. Now here 0 happens to be the first symbol of the input alphabet, 1 has to be the second symbol of the input alphabet. So I for 0 will be 1 and I value for 1 will be 2. So using the formula E of AI, 0 raised to I plus 1. So using this formula I have to now find out what is E of 0, E of 1, where I happens to be the index page. Okay, so let's start. Okay, now E of 0 first, E raised to 0 I plus 1 now. So E raised to I. Now for 0 I is 1 and 1, so it is E raised 0 raised to 1 plus 1, it is not E raised to, so 2 zeros. Now E of 1 is 0 raised to again I plus 1. In our case, what is I for 1? For 1, I is 2, because it is the second symbol of the alphabet set, so I is 2. So this can be written as 0 raised to 2 plus 1, so you will get 3 zeros. So this is how we have encoded each input symbol, whether it is a blank symbol or any valid symbol. Next you have to encode the states. Okay, let's begin with encoding the halting state HA. Now encoding for the halting state HA, if you can remember, okay, the formula says encoding for the halting state is single 0. Encoding for halting with reject state is 2 0, but in our diagram, in our Turing machine that is given to us, we don't have HR state, so this will never arrive. So encoding for HA is 0, correct? Single 0. Now encoding for other states Q0, the formula is 0 raised to I plus 2, correct? Now let's see, Q0 happens to be the first state, so I is 1, Q1 happens to be the second state, so I is 2, Q2 happens to be the third state, so I is 3, and we have already encoded this HA, so you will not be again finding out. So for Q0 I is 1, for Q1 I is 2, Q2 I is 3. So the formula is 0 raised to I plus 2. So this is Q0 I is 1, so 1 plus 2, so you will get 3 zeros. Encoding for Q1 in the similar manner is going to be 0 raised to I plus 2, and in our case now, since Q1 is the second symbol, this will be 2, I is 2, so 2 plus 2 is 4, so you will get 4 zeros. Encoding of Q2 happens to be the third symbol. Okay, so I is 3, so 0 raised to I plus 2 will become 0 raised to 3 plus 2, so you will get 5 zeros. So this is how encoding of all the states. So this is the encoding for all the states. This is the encoding for all inputs. Now what remains is the encoding for the head movement. Stationary 2 zeros, left 3 stationary single 0, left 2 zeros and right 3 zeros. So you can write it as it is. Encoding for stationary is a single 0. Encoding for left movement is 2 zeros. Encoding for right movement is 3 zeros. Encoding transition T1. Now what is T1? Transition. So this is our transition T1. So encoding for transition T1 using the formula, which is encoding for Q0 with 1, encoding of delta separate with 1, encoding of Q1 separate with 1, encoding of delta separate with 1, encoding of right movement separate with 1. So this is the formula. Now we have to only apply those formulas, and we have already calculated the values of encoding values of different inputs and states. So just for a reference, I have pasted it here. We will be using it. Now what is encoding for Q0? Encoding for Q0 gives you 3 zeros, right? So you will get 3 zeros. Then separate with 1. Then what is encoding for delta? Encoding for delta gives you single 0. Again separate with 1. Then encoding for Q1. Encoding for Q1 gives you 4 zeros. Again separate with 1. Then encoding of delta. Encoding of delta gives you single 0. Correct? Then separate with 1. Encoding of right movement. Encoding of right movement gives you 3 zeros, ending with 1. So this is E of T1 that we have obtained. Okay. So this is that E of T1 that we have obtained. So I am going to mark this. It's the encoding function value for T1. Okay. Now similar fashion I will find out encoding transition T2. So if this is a transition T2, then encoding for T2 can be written as encoding for Q1 separate with 1, encoding for 1 separate with 1, encoding for Q1 separate with 1, encoding for 0 separate with 1, encoding for right movement separate with 1. Okay, now let's write the values. Okay, now what is Q1? Encoding for Q1, just substitute the values. Encoding for Q1 gives you 4 zeros. Then there is 1. What is encoding for 1? It gives you 3 zeros. So write 3 zeros separate with 1. What is encoding of Q1? Encoding of Q1 gives you 4 zeros. separate with 1. Encoding of 0 gives you 2 zeros, separate with 1. Encoding of right moment gives you 3 zeros and separate with 1. So what you have found out is encoding of T2, transition T2. This also I am going to mark. Fine. Then, so encoding for transition T3. So encoding of T3 can be then written as encoding of Q1 separate with 1, encoding of 0 separate with 1, encoding of again Q1 separate with 1, encoding of 1 separate with 1, encoding of right moment separated with 1. So just substitute the values of encoding functions from here. So E of Q1 happens to be 4 zeros separate with 1. E of 0 happens to be 2 zeros separate with 1. E of Q1 again is 4 zeros separate with 1. E of 1 again happens to be 3 zeros separate with 1. E of right moment happens to be 3 zeros, finally separate with 1. So this is encoding for T3. Yes. Similarly, we have to find out encoding for T4 as encoding transition T4. So encoding for T4 can be then written as encoding for Q1 separate with 1, encoding for delta separate with 1, encoding for Q2 separate with 1, encoding for again delta separate with 1, encoding for left moment separate with 1. Substituting the values, Q1 gives you 4 zeros, encoding of delta gives you single zero, encoding of Q2 gives you 5 zeros, encoding of delta gives you single zero, encoding of left gives you 2 zeros, ending with 1. So this is encoding of T4 that we find. So these are the strings that we get. Yes, so this is how encoding for T4 is done. Then encoding of T5, transition, encoding transition T5. So this is transition T5. So encoding for T5 will be E of Q2 separate with 1, E of 0 separate with 1, E of again Q2 separate with 1, E of 0 separate with 1, E of left separate with 1. So encoding of Q2 is 5 zeros. Then encoding of 0 will be single zero, encoding of Q2 again is 5 zeros. Encoding of 0 gives you 2 zeros, encoding of left gives you 2 zeros, ending with 1. So this will be encoding for T5. Then encoding transition T6, encoding for transition 6 can be written as encoding for Q2 1, encoding of 1 1, encoding of Q2 1, encoding of 1 1, encoding of left 1. Now encoding of Q2 gives you 5 zeros, encoding of 1 gives you 3 zeros, encoding of Q2 again gives you 5 zeros, encoding of 1 gives you 3 zeros, encoding of left gives you 2 zeros, ending with 1. So this is encoding value for transition T6, this value. And finally encoding for the last transition T7. So encoding for transition T7 will be encoding for Q2 separate with 1, encoding for delta separate with 1, encoding for halting state HA separate with 1, encoding for delta again separate with 1, encoding for stationary separate with 1. Now Q2 gives you 5 zeros. Encoding of delta, as you can see, gives you a single 0 separate with 1. Encoding of halting state HA gives you a single 0. Encoding of delta gives you a single 0. Then encoding of stationary moment also gives you a single 0 separate with 1. So this is the smallest value, I think. Encoding of T7. So these are the different encoding values. So now we have to do encoding for the Turing machine. Therefore, encoding T1. Now the formula that is given to us, okay, I'll just write the formula. Encoding for Turing machine T1 is nothing but first encoding of the start state Q0 separate with 1, and then encoding of each transition, encoding of T1, encoding of T2, encoding of T3. Okay, everything separate with 1, don't forget. Then encoding of T4, encoding of T5, encoding of T6, encoding of T7 separate with 1. So each term separate 1. So finally encoding of the given Turing machine T1 is, first we'll find out what is encoding of Q0. As you can see here, encoding of Q0 gives you 3 zeros separated 1. Then you have to just replace this encoding function with the corresponding values that we have marked in the boxes. Okay, separate, and don't forget to separate them with 1. So that would be the final answer of encoding of Turing machine T1. So this is how universal Turing machine works. Okay, so this was the last concept in your unit 4. Okay, before we end this video, one small note. Unit 4 is one of the smallest units compared to all other units. Okay, so try to solve more problems on Turing machines. Try to solve problems on single tape Turing machines. Multi-tape Turing machines, variations of Turing machine that we had seen in the last video, you get theory question on that mostly. Okay, you don't get problems on variations of Turing machine, you just get theory questions. On universal Turing machine also you get theory question, and they might ask you like in this case, they might give you a problem and they might say to encode a particular Turing machine. So this is a very simple task, right? So with this I would like to end my lecture.